to educator.com, and today's lesson we're going to cover containers. In particular, we're going to cover a certain type of container called a vector. So we're going to cover containers. It's a data structure that holds data for you, that you can put data in, you can take the data out, do various things with it. And there's different kinds of containers. In particular, this lesson, we're going to cover vectors. There are other types of containers we'll cover in another class. So we're going to show you how to declare a vector to contain a certain data type. We're going to access the data in the vector. We're going to add data to the end of the vector, and if necessary, the vector will grow to accommodate your new data. We'll get information about the vector. How big is it? That sort of thing. How big can it be? We'll change the vector specifics, such as capacity. We'll say we need this vector to hold more. We'll learn about an iterator. It's a type of object that iterates through the elements. 1, 2, 3, 4. We want this element, the next element, etc. We can also use those iterators to do different things, like we want to copy these from this iterator to this iterator from that vector and put them into a different vector. Or we want to take from this iterator to this iterator and erase those elements out of that vector. Or we can insert into the middle, and if necessary, we'll allocate memory and move the data over to accommodate the new data, and how to initialize a vector at compile time. All right, there's different types of containers, all kinds of different types. We're going to cover a few. Today we're covering the vector, which is essentially an array, but it's specifically a dynamic array whose size can change as necessary. Unlike an array, a regular standard array, you say, okay, here's 27 objects. This is my array. You need 30 objects, you're stuck. With the vector, you say, we need 30 objects. Fine, we'll stick in 30 objects. We need to allocate more memory, we'll allocate more memory. What we'll cover in the next lesson are things like lists, set, maps. The thing about a list as opposed to a vector, you can do sequential access, but you can also insert data into the middle quickly. Whereas a vector, it depends. You put it in the middle, it's got to take from the middle to the end, it's got to move it over. That takes time. List, stick it in the middle, it doesn't matter. Same amount of speed, no matter where you put it at the beginning, at the end, in the middle, which is the advantage of a list. Set and a map, you have faster access. So you can have a key. It's like looking up something in a dictionary. You want to look up the word boat. Well, you move to the B section, and then from the B section you move to the O section, B-O, and B-O-A-T, and then you can find it quickly. You don't have to start at the beginning of the dictionary at Albuquerque, and then go word by word by word until you find it. With an array, that's what you have to do. You start at the beginning and you keep going one at a time until you find it. So a vector or an array is not very fast for access. A dictionary type lookup, whereas sets and maps give you the faster access. We're going to talk about those in the next lesson. For vector data access, we will look at the access methods for the first element, the last element, or get a specific element. We want the nth element of a vector. For that, a vector is very good. You cannot easily, with a list, set, or map, say, I want the 12th element. Whereas with a vector, 12th element, here you go, 12th element, no problem. Now, iterators, it'll be a new concept. It's something where it's a separate object, acts like a pointer, that says, okay, this is the beginning of the vector, this is the next element, this is the next element, this is the next element. So the iterator iterates through the vector from the beginning until it gets to the end. So it's an object that facilitates sequential access. And we also need to get information about a vector. So there's some methods that give you data about, such as its count, how many are in there. It's also called the size. There's the allocated size, how much can you put into there, etc. All right, so here we're going to talk about vectors. The elements are in, like an array, they're in the sequence. Once they're in there in that sequence, they will stay in that sequence unless you go in with programmatically decide to change things around. So it's just like an array, except the memory is allocated dynamically. Now, the elements may be accessed with a numeric index, just like an array, exactly like an array, or you can call the at method. And the advantage of the at method is there's some runtime checks for you. You can use the iterator. You can add or remove data at the end. It's cheaply at the end. So if you need to add at the end, you add at the end. You need to allocate more memory, you allocate more memory. In the middle, it's not so cheap. Like I said, you have to move things over to accommodate it. So you can add or remove data anywhere in the vector, but you remember, if you put it in the middle, it is going to have a cost. You add it to the end, it might have a cost. Depends on whether or not it has to reallocate memory. Now, if it has to reallocate memory because the vector's gotten larger, because you reserved more space for it, or because the size has actually grown, that can be expensive, because the system may have given you memory in a particular chunk, allocated a particular block, and then the block right next to it has been allocated to something else. So if it needs, if it hasn't allocated the part right at, let's draw a little quick picture. Let's say it allocates this much space, and you use that much space. There's space after it's unused. I need more space. The system says, oh, we've got more space right there. So we'll just give you the more space there. Not a problem. But if this space after that might get moved, allocated to something else. Now I need more space. Oh, well, what it has to do, since this space has been used already, it will have to allocate some memory somewhere else in the system, and then it has to copy all the existing data over to the new data, and that's time consuming. So we're going to cover some methods where you can say, I think I'm going to use this much space, and you can reserve that much space so that you can avoid the possibility you may have to reallocate more memory. So the way we declare a vector of a specific type. That type can be a standard type like int, double. It can be a structured type. It can be a class type. So you do have to include the vector definition in your compilation unit in order to use vectors. Now there's a couple of concepts we need to look at. There's a size and there's a capacity. The size is how many elements are currently in the vector. The capacity is the largest size that can be put into the vector without requiring a reallocation. So here's how we declare a vector. We have the keyword vector, your less than symbol, the type of the data that's going to be put into the vector, your greater than, and then the name of the variable. Like so, let's say we have a integer vector. So we'll have vector int, and then the name of it, let's call it v2. So now we have a vector. This particular declaration will give us a zero-sized vector called v2 into which you can store integers. So this declares a variable of vector of type. Like I said, this type can be any type that you like. This particular declaration gives you a size and capacity of 0. You can say, wait a minute, that's the largest size. I need to put something in it. Don't worry about it. When you put something into it, if it needs more, if it can get more, it will. So we have here's a particular initialization. We have an initial size and initial value. So let's put that example here. Let's say we have vector. Let's make that an int also. Let's call this v3 and say we want to have 25. And we want all of them initialized to -5. So this will allocate a size of 25, a capacity of 25. It will go through all 25 elements and set them to -5. So it sets all of it to initial value. It's recommended that you have an initial value, but you don't have to. If you leave that off, it will use whatever the default initial is. If you have a class with a default constructor, it will call that default constructor for each item that it's putting into your vector. Okay, let's get that data out. We've got the data initialized. We've got v2 with 25 integers with each set to -5. Acts just like an array. You use the array operator. So let's say we have v2 of 5. We want to print that out, cout. So -5 will print. So we don't want that to be -5. Let's say v2 of the 5th element. Let's make it equal to 10. Just like array access. You can also use the method call because a vector is an object. It has methods. It's got internal attributes and fields. One of the methods is @. It works exactly like the array operator, but it includes runtime checks. With v2, we declared as 25, remember? If we say v2 of 30, that won't work. It will crash, and you have no way of capturing that crash. If we say v2 at 30, now there's a runtime check. It says, okay, I need the 30th element. How big is this guy? Oh, it's only 25. 30 is bigger than 25. It will throw an out-of-range exception, which you can capture. You can catch that exception. You can catch it. You can do something with it. You can say, hey, something went wrong. There's a bug in the program, or the user gave me bad data, whatever your situation happens to be. But if it's not caught, it will crash just like a regular array operator. And with a normal, regular array, you do not have this facility. So vectors tend to be a better way of handling your arrays of data. Use a vector instead. So we have some other convenient data access. You have front, which returns the first element of a vector. You could just as well say v2 of 0. Back returns the last element of the vector, and for that you could say v2, let's say size -1, because we're still 0 offset. So if you have if you allocated 25, your access is between 0 and 24. If you don't know the size off the top of your head, or you increase the size some number of times, you would take the size function gives you the current size, which would be 25. You subtract 1, it gives you 24. That gives you the last element, or you just call the back method and get the last element that way. Now, there's one thing to be worried about. Be cautious. If the vector happens to be empty, the return of these functions is not defined. You'll get a peculiar crash. You won't have any idea what's going on. So call the empty function to test. That returns Boolean, which of course, if the size is 0, that'll be true. If the size is greater than 0, it'll be false. So you can say if. Here we have an example here. Vector, an integer called myVector. We have a value. We want the first one. We say value is myVector front. But we only want that if that vector is not empty. And if it is empty, then we want to set the value to something. So we set it to something that's not set, which depending on your application, you might want to say value equals -1 or value equals 0, however you want to work it. If you're dealing with a class, you may have a not set value that's hard-coded for your specific class. Whatever you want to use. But the idea is if you don't have some kind of test for this, or if it is possible for your vector to be empty and you don't have a test for it, if you access front or back, you'll get a crash. So let's get some information out of that vector. We've already seen briefly the size. How many elements are currently in the vector? capacity. How many can be in the vector? Now notice the difference between size and capacity. They can be the same. Capacity can be larger than the size. So if I've got room for 2,000 elements in here, that will be our capacity. It's 2,000. But right now I've only allocated 1,000. So okay, so your size is 1,000. And so I need to increase the size. I got 1,000 elements and they're giving me another one, so I need 1,001. All right, fine. Just put in 1,001, and now the size is 1,001. But since our capacity is 2,000, there's room for it. We don't need to do any reallocation. Now, max size is something that's system dependent. It's the largest possible number of elements based on things like the size of the data, the word size in your computer, how much memory is allocated to your application. You can change the capacity, you can change the size, you cannot change the max size. Now, resize is something you can do if I know I'm going to require more space. So, change the size. It used to be 1,000, let's change it to 1,010. So we'll change the size. Now, if it's necessary to reallocate more memory, if it has to change, let's say it's 2,000, our capacity is 2,000. And we need this changes to 2010. It will change the capacity as necessary. So, we need more space, we'll make the capacity larger. It is necessary because of this changing of the size where, like I said in the earlier slides, where we need to move the data to the new memory, it will do that automatically. Now, if you make it smaller, it'll throw away the tail end. So if you declare it to be 100, you've got 100 elements in there, and you set them all equal to, say, let's say make it 10, and you resize it to, let's say, 100, no, 100 is already set. Let's set to 90. Here, I have an eraser. Let's use the eraser. We'll resize it down to 50. Now, everything from 51 on, or actually from 50 on, since we're starting from 0, from 50 to 99 will just be thrown away. Now, if it's a class with a destructor, the destructor will be called for each element that's thrown away. So it doesn't just, so if you're allocating memory in each class, which is very often done, we very often have a destructor in order to free up that memory properly. If you do this to destroy half of your array, half of your vector, it will call the destructor for each one of those items being thrown away so that that memory is released back into the system. So that's resize, that changes your size. Now, to change your capacity, other than changing your size to something larger than the current capacity, you can reserve a certain capacity. So if you have some rough idea how much space you're going to need, let's say that this, I have 2,000 here. Well, no, let's make it 5,000. I know we've got plenty of memory, so we'll call reserve of 5,000, so that when we size our vector to 1,000 and we use all our items, well, we need more. Okay, we'll change the size. We'll increase the size. That's fine. We've got room for 5,000, so you can increase the size as many times as you want, right up to 5,000. You change the size to 5,001, it's going to have to do memory reallocation, or just depend. You might be lucky and the memory right after that is free. So just take that and tack it on to the end. So you want to avoid expensive reallocations, but it's a balancing act. You can't just make it 5 million. Well, don't forget you've got other things that have got to go in the application besides this one vector. So you will have to do some juggling based on your application, based on your needs, to decide what a decent, reasonable capacity is. Now, iterators. You can do a for loop and use the array access, which is, if you've been doing any C, C++ programming for a while, you're accustomed to using the array access. You're accustomed to doing IDX is set to 0. Keep going while IDX is less than the size, increment IDX, and then access that vector using the array operator. And it's comfortable, it's easy to use. Now, one thing I just want to point out, I use unsigned here, unsigned int, only to avoid getting a compiler warning because the vector size method returns an unsigned int. If you have a normal int, which can be negative, the compiler will say, well, this is a normal int being compared to an unsigned int. It will still compile, but you will get a warning. So to avoid warnings, we do want to keep the compiler as happy as possible. I've declared it to be an unsigned integer. Now, this is great for vectors. It's great if you know it's going to always be a vector, but you might want to, at some point in time, you just might decide, well, we need to use some other type of container, in which case the array access won't work. So you can use an iterator instead. So this is how you define your iterator. You have the vector type. We have vector double here, the V1, we have 100 of them. So we have double, we have our name scope operator, and then the object class name iterator, and the name of the variable it, short for iterator, you can call it it1, etc. And now we're getting begin to give us the first iterator that is pointing to the very first element in the vector. And then while that iterator is less than the vector's end, then we'll dereference it. It works just like a pointer. Dereference it and then use that function. So the iterator has the normal increment and decrement operators. So this works it's almost exactly like a pointer, except it's not a pointer, it is an iterator, but you can use it like a pointer. So when you have this method here of accessing each element, we're iterating through the elements, starting at the beginning until we get to the end. So like if you had a class, for example, or a structure, let's just say we had a class. Let's call it, and let's say, let's call it x for want of anything else. We have integer a, integer b, whatever other things are in there. And we define a class, let's call it x2. So we create a vector of that, let's call that, let's do this right down here. Let's say it's a vector of that type, which is x. And let's call that v3. We haven't used v3 yet, have we? So we create an iterator that would be vector x, the namespace operator iterator. And since we used it, let's call that xit. Exciting, isn't it? So we go through here, when we dereference that pointer, you can dereference it like a pointer dereference to a class or to a structure. And by that I mean you can say xit and using the pointer deref to get to the data that's inside that class or structure, or call whatever method is in there. So here's another look at the begin. It returns a forward iterator. So you can iterate in the forward direction, you can iterate in the reverse direction. It's a forward iterator to the first element, or the 0th position. End gives you a forward iterator to one past the end, similar to a vector of the size. And remember, since we're 0 offset, we will go from 0 until less than the maximum. There's rbegin, which is a reverse iterator. So it starts at the last element. And then rend is a reverse iterator that points to the first element, specifically for the purpose of going from the back end to the front end. And since it's a reverse iterator, we increment it with plus plus, not minus minus. So here we're declaring our iterator called rit for reverse. So rit is set to rbegin until rit is less than rend. Go to the next. Don't think of it as increasing the size or the pointer of the reverse iterator. Consider it go to the next element. The next element in reverse order in this case. And we're dereferencing that pointer and just printing it out. Don't confuse any of these with front or back. These return iterators or pointers. Front or back returns the value at the front or at the back. Now we have shortcuts, and I put that in quotes because it's not really very short. It's kind of long. But I'm sure you've used this particular. We have unsigned idx equals 0, where we're declaring the loop counter inside the for loop. And what this buys you is this index. We can access the index of that particular vector, and this idx, this loop index, can only be used inside this for loop because of the scope rules. Anything between the open curly and closed curly braces, this declares it specifically for this loop and nowhere else. You can do the same thing with iterators. So here we have a vector int, the namespace operator, iterator, it is set to the vector beginning. We will loop until we get to the vector end. We'll go to the next iterator on each loop, and then we access what the iterator is pointing to. And it's verbose, which is why I put short in quotes, but it does control the scope of the variable. This it cannot be used anywhere else except inside of this for loop, which gives you a certain amount of protection against all sorts of nefarious bugs that might creep up on you if you happen to use it accidentally somewhere else or someplace where it's not appropriate. And modifying the data. Of course, we can modify the data with the array operator. So here we have a vector A defined to be 200. It will initialize 200 zeros. And we're setting the last one equal to 100. 99, well, 99 is not the last one. That's right dead in the middle. And we're setting that to 100. So it'll all be 0 except A of 99, which is now 100. We can also use the at method, because the at method returns a left-hand expression. It returns a value which evaluates into a pointer, into a memory location of where you can put the data. So we can say A at 102 is equal to 99. On top of that, we have a few other methods. We have pushback. And what that does is it takes a value and adds it to the end of your vector, which makes your vector larger by 1. If necessary, it will make your capacity larger by not necessarily 1. There's a real cute homework assignment in this lesson that I want you to do, where you actually are running pushback repeatedly and then printing out the size and printing out the capacity, so you can find out how it reallocates new memory every time it needs to allocate new memory. It doesn't just increase the capacity by 1. That'd be kind of silly. It will allocate. It'll get you give you 32, and then give you 64, and then give you 128. That type of thing. So that under the assumption that if you're a certain size and you need more memory, just getting one more is probably not going to be good, because you're probably going to need one more again. So it will allocate enough capacity that, under some algorithm that is designed to avoid having to do repeated reallocations of memory. Now, the reverse of pushback is popback. It goes to the last element, throws it away. Your size is shrunk. You shrink by 1. And if necessary, if it's a class with a destructor, it will call that the object's destructor. And if it's allocated memory, that memory will be returned to the heap, etc. Now, notice it doesn't change your capacity. Capacity tends to increase. It doesn't. I don't know of any way of telling capacity to become smaller except to create a new vector. Now, this is one thing you cannot do with an array. you can insert data right smack in the middle of the vector. With an array, you can do it manually by writing your own code to copy everything over. With a vector, it does that for you. So here we're going to do it right at the beginning. We're going to give it an iterator, the beginning, and the new value. Here's our declaration of it. So we have a vector of 100 integers, each initialized to -1. We're going to insert something at the beginning, a 0. So now when we print that out, it will say 0, and then it'll be -1. And the size will now be 101. And the capacity will be, well, whatever it'll be at least 101. It'll be greater than, it'll be 101 or greater to allow you to do another insert. So let's do something in the middle. Let's say you're in the middle of a for loop, and you happen to be chunking along, and right somewhere in the middle, there's something in your algorithm that says, well, we need to insert something right here in the middle. So now we've advanced our iterator, let's say 50. So we'll put a 10 there. And again, that moves everything over by 1. Size is increased by 1. Capacity is increased by enough, at least 1. Now there's another way to get that iterator. So you say, well, at the beginning, we'll just add 50 to it. And this iterator having been defined for this specific vector. So now you'll be 50 into the middle of the vector, and you can, what do we call this? A? All right, we can say A, insert the iterator right here that we've defined, some new value, 2000. So the insert requires the iterator in order to work. And like I said, you can do this with an array. What you'd have to do with an array is yourself to manually copy all the data over and then put the new value in the new location. With the insert method, that's already done for you. You don't have to worry about it, except to keep in mind the fact that there is the time required to copy all the data over. Here's some more operations. Empty, which we've talked about briefly before, returns true if the size equals 0. Erase either a specific position or a first or last. So based on these iterators, you can actually do the reverse of insert. We go to the specific iterator position and erase it. That object will be destroyed. If it's a destructor, that destructor will be called, and then everything else behind it will be pushed over to close up that space. So destructors are called for each element removed. Other elements are moved to take up the space that used to be there. And the size is reduced by the number of removed elements. The capacity is unchanged. Clear is just like erase, except it clears everything. That's like erase from begin to erase end. And again, of course, the destructors are all called. The size is set to 0. And you could say the empty is set to true. Now, you can assign values, takes the first n elements and assign it to a value, or go to the first iterator to the last iterator, and copy those elements from some other vector. And so you have another vector out here. Let's say you've got v1. It's defined however it's defined. Let's say your data in there is 1, 2, 3, 4, 5, etc., 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 etc. And you define your iterator. Let's say it's v1 begin plus 3. I give you your third. So let's assign, let's make another iterator called v2 and assign this iterator and iterator plus 3, so we can get 3 elements, and copy them from v1, from 3, 4, 5, and 6, and copy them into v2. Now you might want to ask, how do I initialize all this at compile time? That's what I like to know, because it's kind of a pain in the butt to write out v1 is 0 equals 10, v1 of 1 equals 20, blah, 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 etc. You fear not, you have a kind of a compile time initialization. Basically what you do is compile time initialization of a traditional array, or normal array. And then you create the vector using that array as your initializer. So it will copy it from that array into the vector. So here we have an example. We've declared 10, 20, 30, 40, 50. We happen to know that there's 5 elements, so we're going from A1, which will be a pointer to the A1 array, to A1 plus 5, which will be a pointer to 1 past. So this is 0, 1, 2, 3, 4, 5. And so it will copy using like from 0 to 0 is less than 5, which will give us from 0, 1, 2, 3, and 4, and copy that integer array into this integer vector. Now, well, what if I don't know that it's 5? Well, you do a little bit of mathematics, or let the compiler do some mathematics. Here we have integer array A2. It's set to 10, 20, and a bunch of other stuff all the way up to 900. And I'm not going to tell you that it's incremented by 10 because that would be cheating. There may be some missing, there may be some extra ones in there, but whatever it is, the compiler will do the counting for you, and it will know how many elements are in the integer array A2. So in our vector, V2, we will let the compiler do the arithmetic to go from the size of the array to how many elements are in the array. And the way we do that is we'll take the size of A2 divided by the size of one element. Now, I happen to put A20 there. If you happen to know the type, you could put int here as the type because it'll give you the size of one integer. In this case, it's 4, usually 4. So however many there are, this is how many bytes there are divided by the number of bytes in one element. It gives you the number of elements. So we're going from A2 to A2 plus the number of elements, and this integer array will be copied at initialization into this vector. Or you can also copy from another vector using the begin and end methods. Or if we assume that v4 was declared somewhere earlier in our code, we can use assign. So we declared v4 and we want to copy v3 into v4. We'll use the assignment to go from v3 begin through v3 end, and that will copy all of those elements from the v3 vector into the v4 vector. Now, one thing to be worried about with running iterators, an iterator can be invalidated if you do something that potentially changes where the vector is actually stored in memory. So these following functions invalidate. You could say, "Well, my code's working." Well, yeah, it's working today. Tomorrow it might not work because, depending on what the system is doing, what your computer's doing with whatever else is running in parallel with your application process, you never know exactly what's going on inside the memory. Clear will definitely guarantee to invalidate whatever iterators you have. Erase, of course, because it moves things over. Insert moves things over in the other direction. Pop back shrinks your vector. Push back increases your vector. Reserve is, okay, I've got 1,000 memory slots right now. I need to reserve 2,000. So I've got a spot right here now with 1,010. I'm going to have to allocate some new memory for your 2,000, which means I'm going to have to copy it from that location to a new location. If you happen to have any iterators pointing into that vector, they're no more good. They're still pointing to the old location. And resize is the same thing. Resize with a reserve might not invalidate your pointers, but don't take that chance. So just be cautious. Don't use your iterators and any of these functions at the same time. Make sure you're finished with the iterator before you do something like this. Or, like for example, using pushback or popback, use an integer index through your loop instead. And I think that contains this lesson for today. Thank you for viewing our lesson for Intermediate C++. I will see you at the next lesson for educator.com.